Today is day 3 over complex numbers. In our lesson, we are going to be solving quadratic equations with complex solutions. Before we get started, however, I wanted to examine some powers of I. The two basic building blocks that we have learned with imaginary numbers are the imaginary unit I, which represents the square root of -1, and I squared, which equals -1. And we're going to see here that we can find a pattern of the factors of both I and -1. Let's start with -1. When we raise -1 to the first power, of course, that is -1. When we raise -1 to the second power, there are two factors of -1, and when we multiply those two factors together, that returns a +1. The quantity -1 to the third power is the product of three factors of -1 and will result in a -1. And you can begin to see that a pattern occurs. 4 factors of -1 multiplied together is an even number of factors, which results in a +1, and 5 factors of -1 results in a -1. And so you can see when you raise, and I can show you this below, -1 to an odd power, the result is -1. When you raise -1 to an even power, the result is +1. So let's go back up here and look at the powers of I. First off, I to the 0, which is not on your sheet, we know anything to the 0 power would be 1. Of course, I to the first is I, and I squared is -1. I to the third could be rewritten as I squared times I, which would be -1 times I, which produces -I. I to the fourth, there are two ways you could think about it. Maybe I squared times I squared. That would be -1 times -1, which is +1. And we can continue this pattern, but what you're going to find is that there is a pattern that occurs with all of these factors of I every 4 powers of I. The pattern repeats itself, and so if you look below, you're going to see this. I to the 0 up here is 1, right here. Then we have I, -1, -I. Then I to the fourth is +1, and then you can see the pattern repeats itself. And there's any number of ways that you can get this, but do you see every 4 outcomes, the pattern repeats? +1, +I, -1, -I. +1, +I, -1, -I. So as a result of that, what we see here is that we can divide our exponent by 4 to figure out where in the pattern we are at. If you divide by 4 and the remainder is 0, that really implies I to the 0 or the outcome of 1. If the remainder of the division is 1, that implies I to the first or the result of I. If the remainder is 2, that implies I squared or the result of -1. And if that remainder is 3, that implies I cubed, which results in giving -I. So take a look down here at the problems below. The first problem you see is taking -1 and raising it to the +32. It should make sense that that returns a +1 because there's an even number of factors of -1. Whereas -1 raised to the 33rd power, there is an odd number of factors of -1, which results in a -1. How about I to the 32nd? Well, you can see right here, let me change the color of my pen, right here, I am dividing 32, the exponent, by 4, which is the pattern. It repeats itself every 4, and 4 goes into 32 evenly 8 times, so the remainder is 0. As a result, that means we'll really have I to the 0, or 1, as our result. How about if the exponent is 33? Well, when you divide by 4 right here, you get 8, but because 8 times 4 is 32, the remainder of that division right here, which is a little off the screen, is 1. So that means in our pattern, we really are I to the first, or I. How about where the exponent's 46 over here? Well, 46 divided by 4, it goes in 11 times with a remainder of 2, which implies I to the second, or negative 1. So this is how we are getting these answers. And then 83, just pulling a larger number, 83 divided by 4, 4 goes into 83 20 times with a remainder of 3. So that remainder of 3 implies I to the third. We need to simply learn I cubed up here is equivalent to negative I. So that's an alternative way to help you simplify powers of I. We can't leave any power greater than 1 in our answers. All right, let's go down and solve some problems here, which are quadratic equations that have complex solutions. So in number 1, we have negative 9x squared equals 36. What I'm going to do here is divide both sides by negative 9. That gives me x squared equals negative 4. And then I am going to use the square root property and take the square root of both sides. And that gives me x equals plus or minus, and it would be 2i. The negative for the square root of negative 1 is in there, times the square root of 4, and the square root of negative 1 is I, and the square root of 4 is 2, and we write that 2i, not I2. We're not playing Battleship. All right, number 2, same idea. We have 1/8 x squared minus 4 equals negative 10. We're going to add 4 to both sides of that equation. That gives me 1/8 x squared equals negative 6. And then I would multiply both sides here by 8. And when I do that, that gives me x squared on the left equals negative 48 on the right. Of course, at that point, I'm going to use square roots to help me. And that gives me x equals plus or minus, and the square root of negative 48, that can be broken into negative 16 and 3. And we know that the square root of negative 16 is going to be 4i, again, the square root of negative 1 times the square root of 16 times the square root of 3. All right, our final example. 2x squared plus 26 equals negative 10. I will subtract 26 from both sides. That gives me 2x squared equals negative 36. Divide both sides by 2, so x squared equals negative 18. Take the square root of both sides, and hopefully you recognize the perfect square factor in 18 would be 9. I'm going to put the negative with the 9 because when I take the square root, I'm going to have to include I with my factor. And I get plus or minus 3i times the square root of 2. There's one final problem I want to do that is similar to those in your homework, at least a couple in your homework, and that's the problem page 250, number 9. What they give you are two equivalent complex numbers. On the left, we have 3a plus the quantity 4b plus 2 times I equals 9 minus 6i. So what we have to understand is if these are two equivalent complex numbers, the real parts have to be equivalent, namely that means 3a and 9, and the imaginary parts have to be equivalent, the 4b plus 2 and the negative 6. So what I'm going to do is I'm going to write two equations. The first one setting the real parts equal, and when I solve there, I get a equals 3. And then for the imaginary parts, I'm going to set their coefficients equal. So 4b plus 2 equal to negative 6, which means 4a would equal negative 8, and a would equal negative 2. And that's how you solve problems where you have two equivalent complex numbers. There is one problem that's a little more complicated because a and b are both in each quantity, which means you're going to need to use a system of equations, but I'll let you think that over as you go through the homework. So your homework, you can see that below. This can also be found on Canvas, but pages 250 to 252, numbers 36 to 41 all, 45, 47, 48 to 56 all, and 75 to 77 all. Just as an FYI, block days are going to be Wednesday and Thursday, normal block days, and Friday is going to be a 7-period day. So that you are aware, we will be quizzing on Friday over complex numbers and factoring. Have a great day. Thank you.